All right. Can you see the screen?
Yes.
Okay, so today we'll be done with the topic of chapter of matter altogether, ideal gases, temperature. Today the goal is to talk about internal energy, where we'll discuss first law of thermodynamics as well. So whatever we did in the last lecture, we discussed two main things: specific heat capacity, or you can say heat capacity and latent heat, right? Or specific latent heat, and then we have two versions of it, fusion and vaporization, right? So is there any question from those topics? No questions. All right. Okay. So then we will start with the topic of internal energy. Internal energy. All right. So let's quickly recap. Not really recap, but we have been talking in terms of the. Okay, so there's this problem with Zoom. Okay, yeah, now it's fine. Okay, so we have been talking about particles, right? We have been talking about atoms. I've been calling them atoms. You can say particles or whatever. And these particles have been carrying energies, right? So, for example, I have a system of particles, and these particles, they're sitting around. They'd be carrying some potential energy, and they'd also be having some kinetic energy. So every particle in a system has these two energies. You can say a mixture of these two energies, really. And we know that the kinetic energy has been telling you about the temperature of the system, right? And the potential energy tells you about the state of the system, right? Now, it is important to note that not every particle will have the same amount of kinetic and potential energy, the same mixture of potential and kinetic energy, right? So for example, what I'm saying is, suppose this particle has a kinetic energy of suppose 2 and potential energy 1, then it's not necessary that this particle will have the same mixture, right? It could have some other kinetic energies, 3, and potential energy, anything, right? So 0 for, I mean, I gave that example, so I should maybe say this is 1 and this is 2, or anything, right? So every particle has different mixture of kinetic and potential energy. What I'm trying to say is that these energies are randomly distributed in a system, right? So what is internal energy then? Internal energy is, well, the name kind of gives you a hint. It is the sum of these two energies in the system, right? So I can, if I represent internal energy with the symbol U, then I can say that internal energy is the sum of the kinetic and the potential energy, right? So is that clear?
Yes.
Okay, so then I can define internal energy with, let's just give it a statement and say that internal energy, I'll just use U. Internal energy is the sum of the random distribution of these kinetic and potential energy. So I'll just write it as K plus P, where K is kinetic energy, P is potential energy, and I'll give it a subscript, a random distribution, right? So the sum of these kinetic and potential energies is randomly distributed with all the particles in this system. All right, so that's your internal energy. Now, if I have this thing, if I know what an internal energy of a system is, then I can check how would it behave upon playing with the parameters of the internal energy, which are kinetic energy, potential energy. What can I do to the system to cause a variation in the internal energy, right? So what are two things that I can do to, suppose that you want to increase internal energy? How would I do that? One of the ways is if I heat, I'm talking practically, right? So you can say that increased kinetic energy or increased potential energy, that would obviously increase the internal energy of the system. But okay, so how would I increase the kinetic energy? Anyone? Practically, what should I do to the system to increase its kinetic energy?
Increase temperature.
Increase the temperature, right? And how would I increase the temperature? By simply heating my system, right? So I'll apply some heat and the temperature would rise. Now, temperature is a measure of velocity, you can say, or the kinetic energy of these molecules. And so the kinetic energy would increase, and if kinetic energy increases, obviously you will increase, right? Another way to increase this energy is to cause some change in the state of the system, right? By state of the system, I'm talking about the potential energy. So for example, if the system is sitting still, well, let me give you an example, right? So here I have a container, here I have a piston, which I can move forwards or backwards, and here I have some gas molecules, right? Now, if I push the piston to the right, I'm compressing the gas, right? I'm forcing these molecules to come together. I'm decreasing the volume that these molecules have to sit in that volume. So that volume is decreasing. I'm compressing the gas. What that means is I'm changing the state of the system. I could also pull the piston backwards, and I'm therefore giving them more volume to sit inside. And that would mean that I'm expanding the gas, right? So the gas can expand because it has more volume to sit inside. And again, that means that I'm changing the state of the system. Now, if I change the state of the system, I am changing the internal energy of the system. So if I want to increase the internal energy, I will do it by doing some work on the system. So if I do work on this system, I'm changing the internal energy in such a way that it will increase, or the state of the system is being changed so that the internal energy, the total energy, you can say, of the system is increasing. So until this point, is everything okay?
Yes, sir.
All right, okay, good. So having this knowledge now, we can move on or really define or talk about the first law of thermodynamics. Basically, this thing is leading towards the first law of thermodynamics. There is also something called as the zeroth law of thermodynamics, and that's essentially temperature, the definition of temperature, which we have talked about in the previous lectures, right? We have where we define temperature as a field and all of that, right? So that's known as the zeroth law of the thermodynamics. Of course, by the time first law, second law, and third law, these were developed, and we found out that, you know, we need to define temperature as that temperature is the most essential thing in defining further laws. So they went around and they said, okay, let's just define as zeroth law of thermodynamics, where we define temperature, right? So then we have this first law of thermodynamics after that. And the first law of thermodynamics is really talking about internal energy of the system. You can think of it in multiple ways, but at this point we'll be thinking of it as uh, how can I change the internal energy of the system, or how does the internal energy of the system changes? So I can just define this first law of thermodynamics with an equation which says that the change in internal energy of my system is going to be equal to the energy that I'll supply to the system. And how do I supply energy to my system? Anyone? How
By
do I give
heating
my
it?
system? By heating it, exactly, right? So you heat the system, and heating is essentially just giving energy to the system, right? So you heat the system, you supply some energy, and I'll define that heating with Q. Some heat, so I have positive Q, and then I'll do some work on my system. So in turn, the change in internal energy can be caused by either heating the system or by changing the state of the system, right? As we have, and we have talked about these two things over here, right? So that's why I said that these two things lead to the first law of thermodynamics, which you can then put it into a shape of an equation, which is this equation, right? And here W is the work done, right? So then what is first law? First law is telling you that how can I change the internal energy of the system? So my system is sitting there and I just feel like I want to change its internal energy. What can I do to it? I can do some work on this system, or I can heat the system. That will change the internal energy, or I can do both of them together. Now, if I heat the system, suppose, you can play around with this equation in some ways. Suppose that I give my system some heat, which is plus 10, right? Whatever, joules, anything, right? So just take care of the units. And I do some work. Well, let's say that we'll define the convention for doing the work on the system or work done by the system. We'll define the conventions for that in a moment. But suppose that the work done is minus 10, right? Now, if this is the combination that I'm going for, so I'm giving it heat, which is of, let's give these units joules, right? Joules. So suppose you're heating the system by 10 joules and you're doing the work that it's minus 10 joules. So you can say that you're not doing, the system is doing the work, which is minus 10 joules. That would keep the internal energy. What would be the what effect would this have on internal energy? Anyone?
Sorry, could you repeat that?
Yeah, I'm just saying that suppose that I heat the system and I'm making measurements. So I say I heat the system by 10 joules, and the system does work on the environment of 10 joules. So that would be minus 10 joules. So what effect would this have on the internal energy of the system?
None.
Yeah, it would have no effect, right? So the internal energy of the system would remain constant. So you can just play around with this equation, put some values and see, if I do this and if I do that, really, and what would happen to these variables. And once you do that, you get some of the interesting things come out, and you can play around with those equations. Anyways, so this would cause no change in internal energy. All right, so that's this, right? And we can again talk in terms of this piston and a gas. So I'll just visualize this first law of thermodynamics for you now. So that's what I'm going to do. I'm going to visualize this first law of thermodynamics. So let's just give it a heading: visualization of first law. Now suppose that we have this system where you have again a container, and there's a piston like this that you can move around like this in these directions. Suppose there is some gas filled in this container, right? So this, at this point inside here, there will be some volume V, right? And suppose that well, I should have drawn this a bit more, larger. So what do? I'll draw it again, right? Just give me a second. Okay, so let's draw it something like this. This is the container, and here I have my piston, which I can move in these directions. And now suppose that there is some, I'll just divide this, right? And there are some molecules of gas randomly, having some fun in this region of the container or cylinder. And suppose that where the molecules are sitting around, that volume is V, and this side is of the length A. And now suppose now what I can do is I can move the piston in or out, right? So suppose if the piston was initially over here, right? Initially over here. And then what I do is I take this piston and move it outside, right? So I'll just remove all these lines now. So I have moved the piston to the right. So that leaves some volume for these molecules to occupy. And the distance that I move the piston outwards, let's call it delta x, right? So I have moved the piston outwards by a distance of delta x. So suppose now I'm talking in terms of I'm moving the piston. What other thing can I do that the piston kind of automatically starts moving outside to the right, really? Is there something that I can do to this system so that the piston which was over here would automatically start moving to the right? Can I do something to this system so the piston starts moving to the right?
Increase the temperature.
Increase the temperature, right? So heat it. So when I heat it, what will happen? These molecules will start pushing against the piston, and that would force the piston to move to the right. So basically, I'm heating the gas, and when I heat the gas, the volume that it occupies is going to increase, and we're saying that that increase in volume is this delta V, right? Now note that heating the gas does not change the pressure, right? By pressure, I mean the atmospheric pressure. We are still at the atmospheric pressure because outside this thing, there is some pressure, obviously, right? And that pressure is just 1 atm. And that pressure has been kept constant. Now, if the gas expands, the pressure is obviously pushing the piston inwards, the atmospheric pressure. So if the gas expands or the molecules expand or move to the right to push the piston away, they have to do some work against this pressure, these lines that I have drawn, right? So it has to overcome that pressure to move the piston to the right. Is that clear for everyone?
Yes, sir.
All right. So what is happening? The gas is doing some work against this atmospheric pressure, right? Now, when the gas expands, it does that work, and you can write that work as work done. We know work done is defined as force times distance, right? So you apply some force, and if it moves, the object moves, then work is done. If it does not move, then no work is done. That's how you define work in physics. Scientifically, you define work like this, right? Now, of course, when the gas hits against this piston to move it to the right, it is applying some force, on the piston. So that's the force that I have over here. And the piston moves from this side, it moved to the left by a distance of delta x. So the piston has moved because the gas applied some force on this piston, and that distance was delta x. So this W is the work that is done against the atmospheric pressure by the gas, right? The gas did this work to move the piston away, and it had to do that work against the atmospheric pressure, because atmosphere was only the hurdle in this thing, where it was the atmosphere was keeping this piston at this point. And so if the gas does some work, it pushes away, so it has to really do some work against the atmospheric pressure. So that's clear?
Yes, sir.
All right, great. So now we know, how can I define this force? We're talking in terms of pressure as well, right? So this force, remember, is the force on the piston by the gas molecules. So if I know that force is pressure times area, right? So what pressure would this be? This would be the pressure that is exerted by these gas molecules on the piston, not the atmospheric pressure, but the pressure which is exerted by the gas molecules on the piston. So that's this pressure. What is this A? A is that area of the piston, which is the cross-sectional area of the piston, where this area, right? So if you imagine it in 3 dimensions, really, so it will be a plane-like surface which will have some area A, and that's this thing, right? So the pressure is being applied on this area A, right? Because it's being applied on the piston, right? And the piston has the area A, so the molecules are striking. If I draw it over here, the molecules are striking this area, right? So this area, the front side of the piston. So that's the area of the piston. And of course, delta x, we have already defined, it is the distance that the piston moves away or moves from its position. So having this at our disposal, then we can define the work done as P pressure of what? Pressure of the gas, right? And A, area of the piston, the cross-sectional area of the piston, times delta x, which is the distance that the piston moved. Now, we know that area times another degree of freedom. So area is, suppose if I have area is just x times y, so it's a 2-dimensional thing, 2 degrees of freedom. Volume is x, y, z. This is a 3-dimensional thing, or you can say 3 degrees of freedom. When you combine 3 degrees of freedom, you get a volume. Combining 2 degrees of freedom, you get an area, right? So that means area times delta x would be a quantity like volume. So this gives you expression for work done, which is P times V, or really P times delta V, right? The change in this volume, right? This volume, because it's this distance that it moved. So up until this point, is there any question? Hello? No question. All right. Okay, so now we have this thing. Next step is we develop the first law of thermodynamics, right? So let's apply that first law of thermodynamics to this entire situation, right? So we know the first law of do I have space down? Okay, so I'll try to do it over here. And now I'll apply first law of thermodynamics, right? And the first law of thermodynamics, as we have written it down, is change in the internal energy can be only produced by either heating the system or doing some work on or by the system. Now, this thing can be written as Q plus work done is P times delta V. So this gives you another expression for the change, really the same expression, but like in another form, which is this one. But now here I'm going to define the convention of sign, positive or negative. What does that mean, right? So let's do that on this next page. Now we got this equation that the change in internal energy is the heat that I supply to the system plus some P delta V. Right? Now, I'm going to say that if work is done by the gas on the surroundings or on the atmosphere, then I'll say that the work done is negative, right? So let me define it over here. This is a convention that we define, and then we stick with that. You could have done it the other way around as well, but whichever you choose, you have to stick with that in the rest of the calculations, right? So I'm going to say that if let me write it like this. So if the work is done by the gas, then I have a negative sign, right? Then there is a negative sign with P delta V. And if work is done on the gas, then there is a positive signature with P delta V. So according to this convention, I'll move forward, and then I can rewrite this first law as this thing, minus P delta V. This is specifically written for this situation where the gas was expanding, right? So the gas was expanding, so the gas was doing work by expanding and pushing against the piston. So that means that when the gas expands, then you have a negative signature with PdV, delta V. And if the gas is compressed, that's the opposite of expansion, right? So there's only one opposite. And for that, the signature is positive. So the work done is positive when the gas compresses. So is that clear? All right, great. So let's just before I sum up this signatures, right? Let me just talk about this thing that in this expression delta U is equal to Q minus P delta V. You see that the change in the internal energy delta U is less than the total heat that I'll supply to it. Why is it less than? Because there is a negative PD delta V. So I'm subtracting something from Q. So this thing will be smaller than Q. So I can write this as this implies that this thing change in internal energy is smaller than the heat that I supply. So now think about this. Imagine the situation where I'm supplying heat to the system. I'm supplying heat to the system, but still somehow the internal energy is decreasing. Now, how can that happen? That can only happen if I'm using some of the energy to do work on the gas, right? Or I'm doing work by expanding the gas. Well, I'm not doing the work, the gas is doing this work by expanding itself. And that's why the internal energy, the final internal energy of the system is smaller than the heat that I supplied to the system. right? Because normally you would not expect that. You'd if you're heating something, you would expect its internal energy to go up. But again, that's why I gave you this example over here where I said, where was it? What did I say? Yeah, I said that K plus P, right? So all right, anyways, I don't remember what I said last time, but the thing that even at that time I wanted to communicate this thing, that the internal energy of the system can be either decreased or it can be increased, right? Now it depends. Yeah, I remember what I was saying. So I was just saying that if I have the kinetic energy as some value, I did not write over here. Yeah, over here. So if I give it heat of plus 10 joules, and the work that is being done is minus 10 joules. Now we know why the minus sign, right? Because the gas expands, so you have a minus signature for that. And this, if this is the scenario, then the internal energy would not change at all. And now we have also seen the example where internal energy becomes smaller, right? And that's the case if the gas expands, then the internal energy of the system becomes smaller. Now let me quickly summarize these things, where when do I use a positive signature and where do I use a negative signature. So let's talk first about the change in internal energy. If this change in internal energy is positive, what does that mean? That means the internal energy U is increasing. If it's negative, obviously it means that the internal energy has decreased, right? Because this is change in internal energy. And then we have another quantity, which is the heat that is supplied. And the signatures for this, if it's a positive signature, what does that mean? Positive signature for heat supplied means that energy has been transferred to the system by surroundings, right? So I'm transferring energy to the system, right? You can do that by heating the system, right? And if it's negative, if the heat supplied carries a negative signature with it, then that is really telling you that the energy is transferred from the system. So energy transfer from the system to the surroundings, right? So transferring energy from the system. So you have a system, you take the energy out of the system and you give it to the surroundings. While when it was positive, then you were giving the energy to the system, right? And finally, we have another quantity, which is this work done. And that's where a lot of students, they get confused. If the work done is positive, that means that the work has been done on the system, right? Work done on the system. And if it's negative, then you say that the work has been done by the system. So if I'll give you an example, if this is still confusing, we saw that when the gas was expanding in this piston case, we saw that the gas was doing some work, right? The gas was doing work. The gas was the system and it was doing work. So in that case, the work done was negative. And if instead of the gas moving the piston away, if I use my hand and pull the piston away to the right side, then I am doing work on the gas, and in that case it would be positive. So I hope the sign convention is clear to everyone.
Yes, sir.
All right. Okay, great. So now finally we'll talk about adiabatic expansion and compression, right? And so we need to know what this word adiabat means. Adiabatic expansion and compression. So really, I know what an expansion or compression of gas is, right? We all know now, we are familiar with this thing that expansion is the molecules moving further apart, compression is forcing them to move closer, and so the volume in compression would be decreased and the volume in expansion would increase, right? Adiabatic simply means that there is no energy transfer. Energy does not either enter or leave the system. So without any transfer of energy, I'm expanding or compressing the gas. How can I do that? By simply doing work, right? I'm not giving it. So this just means that Q is 0. That leaves me with, if you remember, we had delta U was equal to Q plus work done, right? But Q is 0. I am not, I'm neither supplying energy nor am I taking away the energy from the system. So then I'm left with delta U equals W. And that is the adiabatic expansion. So if you're given the term adiabatic, adiabatic simply means that energy does not leave or enter the system, right? So that means that when a gas would expand, it would do work on the atmosphere.